is a specific type of inelastic situation for explosions. Because in a sense, take something Mr. Coburn does every year with his seniors is he drops a watermelon or some version of that off of the roof and videotapes the pieces flying out in different directions. So the initial momentum in the direction of where the, like in the plane where the melon hits, is zero because it's moving down. So it just blows up in that direction, and pieces go flying out. Well, you could collect all the pieces, which they do, and measure the mass, and all those mass and velocities should sum up to be zero. So, because the initial momentum of the melon in that direction was zero. So that's what we're going to make use of today. And the same sort of thing happens when you have if you put an M80 shoved into a melon and blow it up. The initial momentum is zero, and then the momentum of all the pieces afterwards should sum up to zero. So this is our inelastic version of conservation of momentum. But many times for explosions, the one side, the initial is zero. So, I mean, that's it. The first part is the conservation of momentum just reversed, right? I mean, it's the inelastic conservation momentum reversed there. And in backwards, because we're starting at zero and blowing it up into pieces and moving and separating those pieces out. So many times it's combined, but the v is zero, and then it's m1 v1 prime plus m2 v2 prime, the mass and velocity of each piece after it blows up. It could be moving. You could put the melon, you could put a firecracker in the melon on a skateboard, roll the skateboard along, and then blow the melon up. And so it would have an initial velocity here for that. And then it would have a mass and velocity afterwards that would be equal to that prior. So the statement we wrote here originally, m1 plus m2 times v equals m1 v1 prime plus m2 v2 prime, looks a lot like the expression for an inelastic collision, except it's written backwards. The objects coming apart or exploding, like dynamite, or firing a gun, or atomic decay. They all qualify as explosions. In most cases, the initial velocity, then the initial momentum is zero, but it's not a requirement. So let's look at some examples of these. Okay, so a 3-kilogram melon is sitting on the floor with a firecracker in it. It explodes and breaks into exactly 3 pieces. A 1-kilogram piece goes east at 50 meters per second. A 1.5-kilogram piece goes west at 60 meters per second. What is the velocity of the third piece? So we have this melon, and it's going to go into 3 pieces. Okay? Now we know that the first piece, the blue piece we'll say, it goes off with an initial velocity, or a velocity after explosion of 50 meters per second. We'll call that plus because it's going in the east direction. Another piece, it goes west at minus 60 meters per second. We want to know what the black piece is going to do, its velocity. Well, because the blue is in the one direction and the green is in the opposite direction, the black is also going to have to be in that linear direction. So we don't have to use vectors with angles. We can just use plus or minus on that, because the total momentum afterwards must sum to 0. So, I mean, because the total momentum before collision is 0, it's going to be equal to the mass 1. Well, it's going to be equal to the mass of the blue piece times its velocity those are the pieces we're looking at, plus, oops, plus the mass and velocity of the second piece, plus the mass and velocity of the third piece. So it blows up in it. All those have to sum to 0 because it was stationary prior. So the blue piece, they said, that went east was 1 kilogram. And that was going what we'll call positive 50 meters per second because it was east. The green piece was 1.5 kilograms, and it was going west at minus 60 meters per second. The minus for the west. The mass of the third piece must be, the total must be 3 kilograms because we were told it was a 3 kilogram melon, so this must be 0.5 kilograms, and we're looking for V3 prime. So we get 50 plus 50 minus 90, because this is 50 minus 90 plus 1.5 V3 prime. Oops, kilograms. I'm sorry, 0.5 kilograms. 50 minus 90 is minus 40. Bring it to the other side. Plus 40 kilograms times meters per second equals 0.5 kilograms V3 prime. Divide 40 divided by 0.5. V3 prime equals 80 meters per second. Okay? Okay, so a second melon, 4 kilograms, is rolling east at 10 meters per second when it explodes into two pieces. A 2 kilogram piece heads east at 40 meters per second. What is the final velocity of the second piece? Okay, so in this case, initially the melon, which will give a red side and a green side, initially it's rolling at 10 meters per second. Okay? But the green, it explodes into two pieces, and the green piece goes off at 40 meters per second towards the east. And we're wondering, what is V of the second piece? So our equation, inelastic equation, is the total mass times the initial velocity equals the mass, well, equals the mass of the pieces times the velocity first piece plus the mass of the second piece times the velocity of the second piece together. So the total mass of the melon is 4 kilograms, and its initial velocity is 10 meters per second. That equals the mass of the green piece, 2 kilograms, times its velocity, which is plus 40 meters per second, plus the mass of the second piece, which also must be 2 kilograms, times the velocity that we're looking for, We don't know yet. So we get 40 over here equals 80 here plus 2 kilograms V2 prime. 40 minus 80 is minus 40. That divided by 2 kilograms will equal our V2 prime. So we can see that our V2 prime is minus 20 meters per second, or 20 meters per second to the west. Okay, and then as a vector example, a third melon, 6 kilograms, is stationary when it explodes into exactly 3 pieces. A 2 kilogram piece heads north at 12 meters per second. A 1 kilogram piece heads east at 15 meters per second. What is the third piece's velocity? So the melon breaks into 3 pieces. And we know the red piece has a momentum we'll call P1 after that heads north. The blue piece has a momentum of P2 after, which heads east. And the green one has a momentum which is off in some direction. We don't know what that is. One thing we do know is that the total momentum before, which is 0, must equal the total momentum after. So it has to also be 0. So the sum of P1's vector, the momentum of P1, plus the P2 vector and P3 vector must be 0. Okay, so if P1, if we take its mass times velocity, we could see that it's 2 kilograms times 12, or 24 kilograms times meters per second. The blue piece, P2, that was going east was 1 kilogram, so it's at 15 kilograms times meters per second because it was going at 15 meters per second. So now we've used our masses and our velocities to find the momentum of the 2 pieces, but we need the third. The momentum of the third piece is the equilibrium of the sum of the vectors of the first 2 pieces, P1 prime plus P2 prime. Because if you sum over here, I'll just draw P1 again, prime, and P2 prime, like that. If you sum those up, you could see that it would equal a vector going off in this direction, like so. And that must be equal and opposite to your P3 vector down like that. So at 180 degrees, and we call that the equilibrium of it. So the first step is to define that P3 is to first find the sum of P1 plus P2 vectors. So it's a Pythagorean since it's north and east. So the sum here will be the square root of 24 kilograms times meters per second squared plus 15 kilograms times meters per second squared. So we can find that sum of 801, take the square root of that, 28.3 kilograms times meters per second. Okay? Therefore, that's its value. But theta, like this, would just be the tan inverse of the y, the red, which is 24, over 15. Or 58 degrees. So now we can figure out what P3 is. So P3 will be the same in magnitude because it's the equilibrium, but it will be at 180 degrees, 58 plus 180 degrees, or 238 degrees down at this. So that's 238 degrees there. That's its momentum. Well, P3 equals mass times velocity, which is V3. So, and the velocity is in the same direction as the momentum. And the mass of it must be, well, we used up 2 kilograms with the north piece and 1 kilogram with the east piece, so that's 3 kilograms. So the mass of this must be 3 kilograms. So we have 28 and 28 divided by 3 is 9.3 meters per second, and it's at the same angle, 238 degrees. And that's topic 6.4.